So let's talk about some methods to strengthen materials. So there are multiple ways and multiple processes in which we can increase essentially the strength of materials, specifically the yield strength of materials. And all these different mechanisms and methods to strengthen materials all correlate to the same things, is making it harder for dislocations to move or propagate. And when that happens, the yield strength increases and the ductility and the strain of failure decrease. So we're going to talk about four mechanisms: work hardening, solute strengthening, grain size strengthening, and precipitant or particle strengthening. So work hardening, or combined with annealing. When you work harden or when you anneal, you also change the grain size of your material as well. So those are interconnected phenomenon. So grain size strengthening is also called Hall-Petch, basically a mechanism as well. So when we work harden a material, when we plastically deform it, we increase the density of our dislocations. A highly cold work material can have up to 10 to 14 dislocations per meter squared. A highly annealed, 10 to the 7th. So that's 7 order of magnitude changes, and our yield strength scales with the dislocation density of the 1/2. And the reason is, when we have more dislocations are closer to one another. You have those compressive and tension regions, those interactions, and that will make it more difficult for those dislocations to propagate. They will pin. You'll have to increase the stress applied to move and force them to glide. So that is really, really important. When you anneal, again, it will scale as to the 1/2, and the grain size will increase as well. Solute strengthening. So I can add solutes. They can be interstitial solutes. They can be substitutional. Your yield strength will scale as the concentration of solute to the 1/2, and you can see that positive, basically, or interstitial, positive volume change, negative volume change that we saw previously. But the key thing is you add solutes, and there's a limit, about 15% or so of solute you can add to a material, an alloy. But that is another way to strengthen materials. They interact with the defects. Grain size strengthening. So as we the yield strength is inversely proportional to the grain size. And this holds up to about 10 nanometers. And the reason is because as you decrease the grain size, again, you get dislocation pileup where they interact. But below 10 nanometers, you basically only have about a dislocation per grain. So that dislocation pileup effect decreases, and hence your yield strength decreases as well. Finally, you can actually precipitate a new phase or particles within your material. When that happens, your dislocation lines have the decision to make. They could either cut through or they could bow around that precipitate particle. So for very, very, very small, or actually, the energy cost for this is, if we cut a particle, we increase surface area. For bowing, you have essentially the energy required, the curvature cost for bowing around. So 1 over r again, and that's your particle size as well. So for very, very, very small particles, we will want to cut because surface energy cost is low. Your curvature is very, very high for small particles. For larger particles, that's creating a lot of surface area. Your curvature costs are minimal as your radius increases. So that is going to be very, very important energetically. And as you increase the fraction of those particles, you can shift this critical radii to the left. So that's it. Next time we will talk about creep mechanisms.